Hi, today we are going to talk about graphs. So what is a graph? A graph is a data structure that consists of a nodes called vertices, like these nodes in the figure, and also a set of edges that relates the nodes to each other. So this edge means that there is a relation between this node and this node. So the application of graph, we can have graphs like in the social media. For example, we can have a node or a vertex for each profile and a links between profiles that are friends. We can have it also in Google Maps to represent the locations, and the edge between these locations represent the road. Also computer networks and transportation. The formal definition of the graph, we have a set of vertices and a set of edges. So the graph is just a set of nodes and a set of links between these nodes. Let's take an example. So this graph has 4 nodes and it has also 4 edges. So the number of the set of nodes is A, B, C, D, and the set of edges as seen here. We have 2 types of graph. The first type is called undirected graph, where the edge has no direction. So I can go from A to B or B from A, there is no specific direction. The other type of graph is called the directed graph. In this graph, the edge has a direction. So this edge means I can go from 11 to 1, but there is no other edge that tell me that I can go from 1 to 11. So this edge has only one way. If I can go from 1 to 3 and 3 to 1, I have to make 2 edges. So this is the directed graph. Also in such situation, we have a graph going from 9 to 9. So in this example, in the directed graph, we have the set of vertices and also the set of edges. But here, when we define the edge, the order is very important in defining the edge because it's directed graph. So 11,1 is different from 1,11. So trees, what we studied before, is just a special case of graphs. So if you can look to the tree, it's a set of nodes and a set of edges between these nodes. So we can look to the tree as a graph. So the adjacent nodes in the graph, it's 2 nodes. We call them adjacent if they are connected with an edge. And a path is a sequence of vertices that connect 2 nodes together. The complete graph is just a graph where each node is connected to each other node. Let's take example. For example, this is a complete graph because node A is connected to B, C, D. Node D is connected to all other nodes. Node C is connected to all other nodes. So that's why we call this graph is complete. So this is complete directed graph. The number of the edges in this graph is n minus 1 for D, n minus 1 edges for B, n minus 1 edges for E, n minus 1 edges for C. So we have n vertices. Each vertices has n minus 1 edge. So the number of edges is big O of n square. In the directed complete graph, we only have one edge connected each pair of vertices, so the number of edges is n multiplied by n minus 1 over 2, which is big O of n square. So the weighted graph is a graph that has weights on the edges. For example, we have edge between Austin and Dallas, and this edge has a number. This number is the weight. This number could represent, for example, the distance between Austin to Dallas, or the time needed to travel from Austin to Dallas, or any other relation between these 2 nodes. We have two ways to implement graphs. The first way is used array-based implementation. So in the array-based implementation of the graph, we can do something called adjacency matrix. So first we have one-dimensional array to represent the names of the nodes, and then we have two-dimensional array to represent the edges. So let's take example. In the previous graph, we can represent it in something like this. So first we have the name of the cities, and here relationship between every city and other city. For example, this 800 means the distance between node 0 and node 5 is 800. So between Atlanta and Houston is 800. If we look to the graph between Houston and Atlanta, it's 800, right? So this is the matrix. So if 0 is in the matrix, this means that there is no edge between node number 4 and node number 5, and so on. So this is the adjacency matrix. We have also linked list implementation. In the linked list implementation, we have one-dimensional array representing the vertices, and also we have for every vertex a list of the neighbors, or we call it adjacency list. For example, for Atlanta, we have a list for all the cities that are neighbor to Atlanta, or has a link to Atlanta, or adjacent to Atlanta. For example, Atlanta is adjacent to node number 5 and node number 6, to Houston and Washington. And here we store the weight from Atlanta to Houston is 800, from Atlanta to Washington it's 600. The same for all other nodes. So this is called the adjacency lists. So we have two ways to represent the graph. The first one is the adjacency matrix. This is good if we have dense graph. Dense graphs mean a graph with a lot of edges. And the memory requirement for this graph is big O of V square, because we will have a matrix of number of vertices multiplied by number of vertices. The nice thing about adjacency matrix is that we can test if two vertices are adjacent easily. For example, if Denver and Houston they are adjacent, I just go for 5 and I see they are not adjacent. So with this, I know that there is no link between Denver and Houston. So this is the nice thing about the adjacency matrix. About adjacency list, it's good in the sparse graph. Sparse graph means I don't have so much edges in the graph. And the memory requirement in this case, if I don't have so much edges, then I don't have long lists here. Okay? So the memory space will be less, will be something big O of V, because I don't store for each node many edges. There is no many edges, so there is no adjacent vertices, not much adjacent vertices. So in this case, the space is less, which is big O of V. And here it's, if I want to know what's the adjacence of a certain vertices, it's easily. I just traverse over the list and I know all the neighbors of a certain graph. So now this is just a simple code to represent the graph in adjacency matrix. So here we have scanner to read the input. First, I ask about the number of nodes in the graph. I ask about the number of edges in the graph. Then I create adjacency matrix, which is n by n matrix. And then I go over all the edges and I ask this edge is connected which vertex to which vertex. So I store U and V for every edge. So it could be like 1, 2. 1, 2 means there is edge between 1 and 2. In this case, I will go to adjacency matrix 1, 2, and I store 1. I go 2, 1, and I store 1. So this is unweighted graph, and also it's undirected graph. Okay, so with this code or this loops, I will update the adjacency matrix with the graph representation. So we need for this code as exercise to write a method to print the adjacency matrix. So take any graph as example, fill in the information of this graph and try to print the adjacency matrix. This is the first exercise. The second exercise, we need to print the graph as adjacency list. So you tell me node 1 is connected to node 3 and 4. Node 2 is connected to node 5. Node 3 is connected to node 2 and 3, for example, whatever. So this is the exercise, and see you in the next video.